Hello. This lecture will cover pages 135 through 145 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 8D, Analyzing AC Circuits with Phasors. Starting on page number 135, Analyzing AC Circuits with Phasors. To analyze an AC circuit, we could use three different methods. The first method is purely time domain. Well, you can see in some of our previous videos that when you analyze it strictly in the time domain, it leads to messy differential equations. And it's you have to have special mathematical techniques to analyze AC circuits in the time domain. So we move on. How about a second method? How about graphing techniques? It's very dependent upon the graphing accuracy. For instance, here we have one waveform, U1, and we have another waveform, U2. It can be voltage or current. And we want to find the total, the result of both of those waveforms. Well, you could take this point and add it to this point and get a point. You could take this point here and add it to that point there and get this point. You could take this point here and add it to this point here and get that point. You can do a point by point, and you could get a total, a sum of two waveforms or three waveforms. But this is very tedious. An easier and much more accurate method, a lot easier than time domain and a lot more accurate than a graphing technique, is to use phasors. That's what the last 2 or 3 lectures were about. All meaningful sinusoidal steady-state analysis is done using phasor form notation with complex numbers. We've already done some of this, but now we're going to get into a little bit of detail, and we're going to work problems. Remember, a phasor is just a radius vector that rotates counterclockwise around an origin with a constant magnitude. So we went ahead and we looked at this in a previous lecture, and we said this right here was a phasor. And this phasor rotated counterclockwise around this circle here. And if you plotted this point for point at the tip of the of this radius vector on the circumference, and you laid it into a complex plane that had a real component and an imaginary component, you could transfer time domain equations very easily into a frequency domain equation. We didn't refer to that as a frequency domain equation, but we are here in this lecture. Again, if we let the forcing function, or what's driving the circuit, be V of t equals V max e to the j omega t, that's that exponential form we talked about, all other voltages and currents will have the same form. So the current is going to be I max times e to the j omega t plus some phase difference. You don't have to assume that the voltage and the current will always be in phase. This is no more than when we said a one sinusoidal drive in the circuit. If it's a sinusoidal waveform, all the waveforms for all the currents and the voltages throughout that network will be sinusoidal. It's not a sinusoidal form we're looking at here. We're looking at the complex exponential form. The only thing that's going to be different here is the magnitude of the current and a phase angle. For example, a voltage V of t can be rewritten in exponential form like this. And here's the real part of that. And it can be shown that the real part in a phasor form looks like this. You don't have to concern yourself too much with this, but since we are working with complex forcing functions, the real part of which is the desired solution, and each term in the equation will contain this e to the j omega t, they drop out. They just cancel out. You can cancel it out here, you can cancel it out here, the e to the j omega, the e to the j omega. You just have a phi left over here. The resulting phasor form is simply, in this case, if you look at voltage, because that's what we were looking at up here, it's that maximum voltage at the phase angle that we've been using all along. This is the proof of that. So that's why we're going to use this phasor form for either current or voltage or impedance when we analyze problems. The above form, this form, is referred to as the frequency domain. And as strange as it may seem, the frequency is not even represented. So in this phasor form, that's referred to as the frequency domain. Just like in the time equations here, v of t was the time domain. When you get down to this form right down here, which is going to be the vector quantity, v max, in this case Vm, it's a vector quantity. It's going to have magnitude right there. It's going to have a direction right there. So I might refer to this as the phasor form, but to be consistent, I'll refer to v of t as the time form. I'll refer to something like this as the frequency domain or the frequency form. But frequency is not even represented here. There's no omega represented in these phasors. General forms. In the time domain, this is what it looks like. In the frequency domain, this is what it looks like. In the time domain, a sinusoid looks like this. In the frequency domain, it looks like this. Keep in mind, when you're in the frequency domain or that phasor domain, that the cosine wave is always the reference. When you see this form and you take it back to the time domain, you always take it back to cosine. That's why when you write this over here, this is in a cosine form over here. So you have to subtract 90. Think about that. You have to subtract 90 here because this is the cosine form. And the cosine is ahead of the sine by 90 degrees. So you have to subtract it to get back to here. Phasor forms in the frequency domain look like this. You already know this. We've already been using it. Voltage is equal to V max at an angle of phase angle associated with the voltage, and I is equal to I max, the angle associated with the current. This is in bold because it is a vector quantity. It has magnitude and direction. This is in bold because it has a vector quantity. It has magnitude and direction. Where phi is the phase angle up here, and V and I are maximum peak values, but you already knew that. Points to remember when working with phasors. The cosine wave is always the reference waveform. Whenever you see tan at an angle of 40 degrees, and you want to take that from that frequency domain back to the time domain, remember it's going to be 10, the peak value, times the cosine of omega t plus 40 degrees. Whether that's current or voltage. Frequency domain, time domain. Solving problems. The solving problem strategy is pretty simple. You're in a time domain. Get it the heck out of the time domain. Because in the time domain, the analysis is horrendous. Move it in to the frequency domain. You end up with phasor algebraic equations. Solve all these phasor algebraic equations in the phasor form through the techniques I showed you in the last video, and then transform them back to the time domain. This problem solving strategy we did in the last lecture. We had the time domain, we got into the frequency domain, we worked everything out in the frequency domain and put it back in the time domain. It works. Here on page 139, I want you to convert the following time functions into phasors. I want you to convert this into a phasor, into the frequency domain, and I want you to convert this voltage V2 into the frequency domain. Keep in mind here when you do the conversion on these, You have to get this in terms of the cosine. This one's already in terms of the cosine. Now, in order to put this in terms of a phasor, in order to put this into the frequency domain, you have to get this in terms of cosine. That's just the rule. So go ahead and work them out and see what you get for an answer. Down here, convert the following voltage phasors into time functions if the frequency is equal to 400 hertz. So the first thing you're going to have to do in this problem is find omega. I want to find omega here first. Then just get it in the time domain. There's the frequency domain, get it in the time domain. And remember, the frequency domain forms look like this. This just converts, that complex frequency domain just converts here to some magnitude to some angle. That's all. So take your time and work through that and see what you get for an answer. Stop the video, do those 4 problems and see if you get this. There's the answers to problem number 1. And once you convert omega, here's the specific time domain answers to problem number 2. For V1 at t, there it is. And for V2 at t, there it is. Phasor relationships for R, L, and C circuit elements. Real quick, I'm going to go through this just to show you. We're going to use this a lot in the next video, and we're going to simplify it, but I want to give you the detail here. If you're in a baccalaureate program, you should understand the detail. Here I have a very simple circuit. I have a voltage V at T that's driving just a resistor, and I have current I at T. I'm going to apply for the voltage V max e to the j omega t plus some phase voltage angle. And it's going to result in the current being I max e to the j, the quantity omega t plus some phase angle for the current. I'm going to use Kirchhoff's voltage law around that loop. And when I do that, I think you can make the substitution and see this. When I move it down, I get it in the phasor form. Keep it in mind what I just showed you here on this page right here. The frequency domain forms look like this. I can use this to go from here to here. And now look how easy it is. I know what V is equal to. I know what I is equal to. And you can see that the resistance, when I solve for R up here, is V over I, which is equal to V over I at an angle of V phi minus VI. Well, why V phi minus VI? Because the voltage is on the top and the current's on the bottom. And the angle in the top is phi V, and you're bringing the angle from the denominator up. You remember how you do that. You just subtract the angle in the denominator when you bring it to the numerator. That's why it's, when you're forming the resistance here, we already talked about this too. It's equal to the phase angle of that's associated with the numerator minus the phase angle that's associated with the denominator. These two angles are the same angles. They'll always be the same angles, so the phase angle is 0. The voltage and the current will always be in phase when it's a purely resistive load. Why will the voltage and the current always be in phase when it's a purely resistive load? Because there's nothing to hold back the voltage, like a capacitor, and there's nothing to hold back the current, like an inductor. Remember, voltage can change instantly across the capacitor, and current can change instantaneously through an inductor. There's no inductor or capacitor up here to hold the voltages of the currents up. So the voltage will be directly in phase with the current, right on top of one another. The only thing that's going to be different is the one waveform is going to have a different maximum value than the others. That phase angle will be 0. And if you don't believe me, on page 141, here's a simple little problem. The following example will prove the voltage and the current are in phase with each other in a purely resistive circuit. There I have all the values. I'm giving you a 6 ohm resistor. I'm giving you V at T is equal to, here's the value. I want you to solve that for I at T. Well, you just put this, it's already in terms of the cosine. You put it in the phasor form, get in the frequency domain, use your Ohm's law, and look at the current. Put it back in the time domain. The current has a phase angle of 75 degrees. The voltage has an angle of 75 degrees. They'll always be in phase. So when you take your phi v minus phi I back in this general expression, you can see they're going to be zero. The phase angle will be, there'll be no angle associated with this magnitude here. The phase angle is zero. That's the proof that when you see a purely resistive load, phase angle is zero and the voltage and current are in phase. You can make up all type of examples here, but you should understand this. We've worked out many problems like this a lecture or two ago. What about if it's a purely resistive load or purely inductive load? When a purely inductive load, there's an inductor, there's the current, there's the voltage. The voltage across the inductor with respect to time is L di dt. Remember that? Voltage across the inductor with respect to time is L di dt, and we're just going to apply the voltage with respect to time. There's the complex voltage form. Here's the complex current form. I'm going to put it into, by Kirchhoff's current law, this rise has to equal this drop. You know, by Kirchhoff's voltage law, the rise has to equal the drop. I'm making the substitution, but in order to find the voltage here, it's L di dt. I have to take the inductance times the derivative of the current with respect to time. That's a simple derivative, and you get this. Bring this j omega L down. This j omega comes down in the front here. You get j omega L here. And the I max is just along as a constant. Simple derivative here, using L di dt. Simplify it down and form your expression. You can see that the voltage in the phasor form, once you drop the exponential forms out, using this technique I showed you here, using this, remember the frequency domain forms, you're going to end up with j omega L is equal to V over I, which is equal to something called the inductive reactance. Well, look up here. It has to be equal to omega L at an angle of 90 degrees. So omega L at an angle of 90 degrees has to equal V max over I max times the angle of V phi minus VI when you take these steps and move them down. That tells you that phi sub V minus phi sub I has to equal 90 degrees. That's the phase angle, is plus 90 degrees. We said if the phase angle was plus 90, it puts it in the first quadrant. Anything in the first quadrant was inductive reactive. Think back from a couple lectures ago. So by looking at this, the voltage leads the current by 90 degrees. Or you can say the current lags the voltage by 90 degrees, either one. Why? Because the current cannot change instantaneously through an inductor. That's why the voltage is leading the current. And if you look, you can see what X sub L is. This inductive reactance is equal to omega L at an angle of 90 degrees. It's the impedance of that circuit. It's purely imaginary. Which leads me to a point here. This term imaginary number, when you're talking about complex numbers, it's imaginary only in terms of the mathematics, but it's very real in real life. This impedance we're going to deal with now can be purely real, or it can be purely reactive, or it can be a combination of both. But there's your complex number. Impedance has a real part, plus or minus an imaginary part. The impedance is the AC resistance we talked about, which is comprised up of resistance plus or minus reactance. Your imaginary term is your reactance, but it's not imaginary at all. It's extremely real in electrical engineering. It's either the effects, the resistance, if you will, the AC resistance of a capacitor, or it's the AC resistance of an inductor. This imaginary number is extremely useful. Extremely useful. It's not imaginary at all. In electrical engineering, it's very real. So what we just showed you here in this example is X sub L is equal to the phasor form of x sub L is equal to x sub L at an angle of 90 degrees, where x sub L is equal to omega L, which is equal to 2 pi FL. The inductance and the inductive reactance are two different things. The inductance is value in henries or millihenries or whatever. Once you take it times omega, you're going to get the AC resistance of it. Or if you take it times 2 pi F, because omega is a 2 pi F, you get the AC resistance. That's the reactance. Very important equation. Inductive reactance is equal to omega L, or 2 pi FL. And it's in ohms. Now, as an example here, what we did was I went ahead and I have an actual example here with an inductor. Very easy problem to work through. You should be able to take this and you should be able to find V sub L with respect to time if you know the current in this circuit. I went ahead and worked the problem out, and there's the voltage. You can clearly see this is the voltage with respect to time once I made the conversion from the form we have here, the frequency form, down to here, the frequency domain, down to the time domain. And you can see if this up here is the current and this is the voltage, you can see that the voltage leads the current by 90 degrees. And it should. It's a purely inductive circuit. We can do the same thing with the capacitor. For a pure capacitance, we do the exact same analysis by Kirchhoff's current law at this point now. The current coming in has to equal the current going out. Here's the current coming in, because we're applying this form up here. The current coming out, the current to a capacitor is C dV dt. It's the capacitance times the derivative of the voltage with respect to time. Well, here's the voltage, just take the derivative of it. Put it in, e to the j phi cancels out, you come down and you end up with a angle of minus 90 degrees, and the capacitor reactance is 1 over omega c. So if you go through the analysis, you can see that the current leads the voltage by 90 degrees, or the voltage lags the current by 90 degrees. Why? Because the voltage can't change instantaneously across the capacitor. That leads to this capacitive reactance up here. I'm just equating values up here in this equation up here. Right here is your X sub C. X sub C. And I get X sub C is equal to 1 over omega C at an angle of minus 90 degrees. Right here. X sub C is equal to X sub C at an angle of minus 90. But what is X sub C? It's 1 over omega C. Remember X sub L? X sub L was simply equal to omega L in ohms. Up here, X sub C is 1 over omega C. That's the value for the magnitude at an angle of minus 90. And we have an equation here. We have an example. This example will prove that the current leads the voltage by 90 degrees in a purely capacitive circuit. So again, here's a simple little example. I have a voltage. There's my voltage in time domain. I'm going to convert that. It's already in the cosine, so I'm going to convert it to the frequency domain. Pretty easy to do. There's my capacitance value. I want to use resistance. I want to use reactance now. So I have to take 1 over omega C. Omega is 3.314. I have to take 1 over 314 times 100 microfarads. That's where I'm getting the value here and inverting it. You'll see that your X sub C is 31.85 ohms. So now I have my voltage. I have my X sub C, I use Ohm's law, and I can calculate the current and go back to the time domain. I'm comparing this time domain current to this time domain voltage up here. And you can clearly see this is plus 105 degrees, this is plus 15. This current leads the voltage exactly by 90 degrees. It's a proof. That the current has to lead the voltage by 90 degrees because the voltage can't change here as quickly as the current because there's a capacitor. In summary, what we're going to have to use from this point forward, and these are just equations you write down, is impedance now is always going to be comprised of a real part and imaginary part. The real part is going to be resistance. The imaginary part is reactance. We know that x sub L is equal to omega L at an angle of 90 degrees. That's in polar form. In rectangular form, it's j omega L. You can go from here to here and here to here. In terms of frequency, it's 2 pi FL at an angle of 90 equal j 2 pi FL in rectangular form. Same thing with x sub c. X sub c is equal to 1 over omega c at an angle of minus 90. In polar form, in rectangular form, it's minus j 1 over omega c. Or you can do it in terms of frequency like I did up here, where omega is 2 pi f. I'm just replacing omega with 2 pi f. So either one of these equations for x sub L in ohms, any one of these equations for x sub c. Remember, c is not the same thing as x sub c. And L is not the same thing as x sub L. This is the reactance. If you have C and you want to get reactance, x sub c is equal to 1 over omega c. Down here, x sub L is equal to omega L. Ohms. Ohms. This is in farads. This is in ohms. This is in henries. This is in ohms. And that concludes this lecture.